Okay, so today we're going to be talking about kind of some word problems. And the truth is, we've been working on word problems for multiple days because each of those lessons that we've been working on does have direct applications to these. And so I think the big thing is that when we're talking about writing an exponential growth equation, there are some formulas and ways that you can use PERT, and that will be expressed at the top. And I think the big thing is for this year, we're going to be focusing on if I ask you to do continuous growth, that's when you use PERT. Okay, there are other ways to use it, but I think if I just say, hey, write the exponential growth equation, this is what I'm going to have you do. Okay, exponential growth really is the simple growth formula where it's going to be y is equal to ab to the t. Okay, and so you know that we can do that with growth and decay. We can also use y is equal to a and then 1 plus the rate over n to the nt, and then we can do y is equal to a e to the RT. So that's for continuous growth, okay, compounded continuously. And so you can basically, if you go to college and take college algebra, or if you take college algebra next year, it's possible that they'll have you use PERT a little bit more. But this year, I think to keep things distinct, we're going to focus on these three formulas. And so so let's look at this. This is not continuous growth, this is exponential growth. And so we're going to say, okay, write this. So at the beginning, there were 20 points. Actually, I lied. In 2000, there were 15.98 million. 15.98. And in 2016, there was 20.61 million people, okay, in Florida. We know it's growing, but we don't know the growth rate. And then the T is going to be how many years after 2000. So we're going to just put, okay, and so because in 2000 to 2016, that was 16 years, we're going to solve this to find the growth factor. So divide both sides by 15.98, so you get 20.61 over 15.98 equals b to the 16. To get plain old b, you're going to take the 16th root of both sides. And so the 16th root of both sides of these is going to give you b is approximately, what do we say here? 1.016. And so to write the exponential growth equation, it's going to be y is equal to, the beginning value is 15.98, that's in 2000, 15.98, and then 1.016, and then to the t. And so the t represents how many years have happened since 2000. And so the question is, if we want to solve this to figure out, okay, when will it reach 25 million? Okay, so here's the thing. We want to figure out if it begins in 2000 at 15.98, okay, when will it reach 25 million? And so I want to practice solving this algebraically. So 15.98, oopsie, I put the decimal in the wrong spot. Let me erase this a second. So let's put down 15.98 and then 1.016 to the t. Okay, so we want to figure out how many years after 2000 will that be the case, and without graphing it. Okay, so yes, graphing it will give the result as well. So if you graph both sides and see where they cross, another option, and in this chapter, I'm going to say, hey, can you solve it using like logarithms or solve it algebraically? So 15.98, because that's what we're trying to work on this chapter. So 25 over 15.98 equals 1.016 to the t. How do you solve it? Change form. So log of 1.016 to the t is equal to the quotient of 25 over 15.98. If you put that in your calculator, math alpha math, you'll solve for t to be about 28.19 years. Okay, so that'd be 2028, or by 2029. Okay, and so, excuse me. So we're looking to write exponential equations and to solve them algebraically using logarithms. Okay, so we're practicing that. So again, we did this last chapter. You begin with 20 bacteria cells, and after 45 minutes, there are 710. Okay, great. We know that they're growing, okay, and so we're trying to say, okay, 45 minutes, and every minute, we're going to say that there's more bacteria than before. Okay, so we need to get some antibiotics. Anyway, 45 minutes is the time. Divide both sides by 20. Divide by 20. And so you've got 710 over 20. You could cross out the zeros if you wanted to, equals b to the 45th. Okay, to figure out what b is, you can take the 45th root of both sides. So the 45th root of both sides. If you look in math, you'll be able to find that. And you're going to get your b is going to be approximately 1.0826. And so our new equation is going to be y is equal to 20. And then 1.0826 to the t, and t is number of minutes, and you should put that t equals number of minutes. Okay, and so then when will there be 1,000 bacteria cells? Again, you can graph both sides of the equation, but let's solve this algebraically. So you get 1,000. That's our result. So 20, 1.0826 to the t. You want to keep quite a few decimals on this. Divide both sides by 20, and then once you do that, you're going to get, let's see, 50. Okay, so 50 equals 1.0826 to the t. Switch forms, it would be log of 1.0826 to the t equals 50. Put the left side in the equation, and t is going to be approximately 49.3 minutes. Maybe by 50 minutes. So you just label your answer. Give me a decimal. And if you feel like you need to round, do it. Okay. The last thing we're going to talk about would be half-life. And I gave you the half-life equation yesterday. And so the half-life of thorium is 75,381 years. Neat. Okay. So if you begin with, let's see, a gram, it says, so if you start with that, you start with a certain amount, okay? And it says, how much will be left after that, that many years, okay? And so you start with 100% of it, okay? And so the question is, how much will be left after this 1,500 years? So the half-life is what you begin with. So I begin with 100%, and the question is, how much is left, okay? And so let's start with 100%, and then we're going to figure out how much is left at the end. And so to the 1,500 over, let's see, 75, I can't read. 75381, if you put that in your calculator, you're going to get 98.63% left. Okay, so that's a simple evaluating the right side of the equation. Okay, and then what they're saying is, okay, can you also find the time it's going to take for 99% to be gone or 100% to be gone? Okay, so we'll start with 100%, and if 99% is gone, that means that 1% is left. Okay, and so then it would be half, and then it would be t over 75,381. Okay, so if you divide both sides by 100, you're going to get 0.01 to the t over 75,381. Switch forms, so it'd be log of 1/2 to the t over 75,381 equals 0.01. If you evaluate the left side of the equation using math, help math, then multiply both sides by 75,381, you're going to get 820 years. Okay, so that's going to be. Now, the question is, when is it going to be 100% gone? And so if you tried that, okay, you say, okay, I want 100% to be gone. Okay, and so if 100% is gone, there'd be 0 left at the end. Okay, so start with 100, end up with 0, and then 1/2 to the t over 75,000. and that would be 381. Okay, if you divide both sides by 100, you get 100, or 0, I mean. And then if we do the change the forms, I'm going to switch colors so you can find it. So I'm going to move up here. We would go, we got t over 75,381. So we'd go log of 1/2 to the t over 75,381 equals 0. Wait, that's not possible. Okay, you can't take the log of 0. Log base 1/2 of 0, that will give you an error. So that means it's not going to actually eventually go away. It'll get so minuscule over time. However, hypothetically, according to our formula, it will never completely be gone. Okay, but I guess that's to be determined if you wait that long to see actually are there traces left, or is that going to be gone? All right, thank you. Have a good day.